So this week we're going to focus on covering lemmas. These are a group of results that say, given a covering of a set by balls, we may reduce that covering to a smaller subcollection with some nicer properties that still covers the set. So one covering lemma that you've seen before is that any open covering of a compact set has a finite subcover. But often we'd like coverings to have a bit more nicer properties, like maybe we'd like to know that the coverings have bounded overlap. Now, before discussing these results, we'll first discuss a similar covering result not for balls, but for cubes, or more specifically, dyadic cubes. So let's review the definition of dyadic intervals and dyadic cubes. So for an integer k, the set of dyadic intervals of length 2 to the minus k are a collection of intervals, each of length 2 to the minus k, whose endpoints are situated at integer multiples of 2 to the minus k that tile the real line. Okay, so each one of these intervals is an interval in delta k, and by virtue of being in delta k, its length, which I denote L of I, is equal to 2 to the minus k. Now, dyadic intervals have a nice nesting property. So if I look at now at the collection of intervals in delta k plus 1, notice what happens. So again, the endpoint, they start at 0 and tile the plane. But now because they have half the length of the intervals in delta k, that means that every interval in delta k can actually be divided into two intervals from delta k plus 1. So on and so forth. So now every interval in here, delta k plus 1, has length 2 to the minus k minus 1. Now I take the convention that the dyadic intervals in delta k have side length 2 to the minus k instead of 2 to the k. And that's because usually in the type of work that I do, I'm usually concerned with what's happening on small scales. So I'd like large k to correlate to smaller intervals. So now that we've defined dyadic intervals, we can define dyadic cubes in any d-dimensional Euclidean space. So the dyadic cubes in Rd of side length 2 to the minus k are all possible Cartesian products of dyadic intervals of length 2 to the minus k. So observe that if I have a cube q in delta kd, its side length, which I denote curly L of q, is equal to 2 to the minus k. Okay, and then the dyadic cubes are just all possible cubes that I get by taking the union over all dyadic cubes of side length 2 to the minus k as I range over all integers k. Now, oftentimes I will just write delta instead of delta to the d when it's implicit from the context what the dimension of the cubes are. So, for example, so just to give a picture, so the dyadic cubes of side length 2 to the minus k, for example, they're going to be a collection of cubes that tile the plane, and there's going to be one whose bottom left corner is situated at 0. And their side lengths are always 2 to the minus k. And these tile the plane, so I keep going this way, this way, and this way. Okay, now, again, the dyadic cubes have a nesting structure in the sense that if I look at the cubes in delta k plus 1, okay, these are still going to tile the plane. But now every cube in delta k plus 1 gets split into 4 squares from delta k plus 1. Dyadic cubes have some nice properties that make them very convenient to work with in practice. So first of all, they have discrete sizes. Any cube has side length 2 to the minus k for some integer k. Secondly, every dyadic cube of generation 2 to the k can be written as the union of 2 to the d children cubes. Conversely, every dyadic cube of generation k has a unique parent cube inside the previous generation. So there's a unique cube in the previous generation that contains q. So these two properties mean that dyadic cubes have a natural tree structure. Moreover, the cubes of generation k cover Euclidean space. And not only do they cover Euclidean space, they also partition it, not exactly, but in the sense that the cubes in generation K have disjoint interiors. More generally, we have the following property that whenever we have two dyadic cubes of any generation, if their interiors have non-empty intersection, that implies that one of them must be contained in the other. Using these properties, we can prove the following covering lemma. So for any collection of, so this should be dyadic cubes. Okay, let Q prime denote the set of maximal cubes. So these are the collection of cubes Q in curly Q that are not properly contained in any other cube from the collection Q. Then the maximal cubes have disjoint interiors, so they are effectively disjoint. And moreover, the union over the cubes in this sub-collection is equal to the union of the cubes over the whole collection. Okay, so let's see how a covering lemma like this is useful in practice. As a motivating example, and an example that we're going to return to as we discuss the other covering lemmas this week, we're going to consider the Hardy-Littlewood maximal inequality. So recall that the Hardy-Littlewood maximal operator is defined as follows. So given a locally integrable function f, the maximal function of f at a point x is the supremum over all averages of f over all balls centered at the point x. So one part of the Hardy-Littlewood maximal theorem says the following. If we're given a function f in L1, then for all positive lambda, the set of places where the maximal function is larger than lambda has measure at most some constant, depending on the dimension of the space, times the L1 norm of f divided by lambda. So this is a very important theorem that has many numerous applications across analysis. One that you may have seen is the Lebesgue density theorem, which says that at almost every point for a locally integrable function, if we look at the averages of f over a point, those averages converge to the value of f at that point as the ball shrinks to zero. So sometimes what analysts do when they're approaching a problem like proving bounds on an operator that's defined in terms of balls is that they might define a analogous dyadic operator defined in terms of dyadic cubes instead, and then prove the analogous result for this operator in order to gain some intuition about the original problem. So what we'll do now is demonstrate how to prove a dyadic version of the Hardy-Littlewood maximal inequality. So the dyadic version of the Hardy-Littlewood maximal inequality that we're going to consider goes as follows. So first of all, the dyadic maximal function of a locally integrable function f evaluated at a point x is defined to be the supremum over all averages of the absolute value of f over all dyadic cubes containing a point x. Then the dyadic Hardy-Littlewood maximal inequality says that the measure of the places where the maximal function is bigger than lambda is at most L1 norm of f divided by lambda. And also observe that there's no constant in front of here. So we actually get an improved version of the Hardy-Littlewood maximal inequality. Okay, so let's go through the proof. Okay, so let's fix some things first. So first of all, I'm going to assume that f is non-negative without loss of generality. Also, I'm going to call this set here E sub lambda. So this is the set whose measure I want to estimate for a fixed positive lambda. Now, let curly Q denote the set of cubes, set of dyadic cubes, for which the average of f over that cube is bigger than lambda. All right, so it's not too hard to show that E lambda is actually equal to the union of the cubes in this collection. So the reason why is as follows. So if I have a point x in E lambda, so if x is in E lambda, that implies that there exists Q. So that implies m delta f of x is bigger than lambda, but that implies that there exists a Q containing x such that the average of f over Q is bigger than lambda. But then that implies that Q must be inside this collection. So that gives me one direction, that E lambda is contained in this collection. Now, furthermore, if x is in Q, is in my collection, okay, that implies that lambda is at most the average of f on this cube, But that means that, so recall that the dyadic maximal function is the supremum over all averages of dyadic cubes containing f. So this is at least the maximal function of f evaluated at x. So that implies that x must be an E lambda, and that proves the reverse containment here. Okay, so now by the previous theorem, if I let q prime equal the maximal cubes in Q, now this is a collection of cubes with disjoint interiors that has the same union. So in particular, its union is also equal to E lambda. So if I look at the measure of E lambda, this is by subadditivity of Lebesgue measure. This is at most the sum over the cubes Q in curly Q prime, the measure of Q. Now, by virtue of Q being in Q prime, and hence in Q, what this inequality tells me, that so for a cube in this collection, if I multiply both sides of this inequality by the measure of Q and divide both sides by lambda, I get that Q, the measure of Q, is at most lambda to the minus 1 times the integral of f over Q. All right, now finally, because the cubes in this collection have disjoint interiors, that means that they only intersect at the boundary. But the boundaries of these cubes have Lebesgue measure 0. So that implies that effectively these sets have no overlaps. The overlaps are measure 0. So that implies that I can pull these integrals all together. So this is equal to lambda to the minus 1 times the integral of the union over all cubes in curly Q prime of f. But this is just at most the integral over all of Rd of f. And then we're done. This is lambda to the minus 1 times the L1 norm of f. So let's make a few observations about the proof. So first of all, notice that if we replace cubes with balls in the proof, this doesn't give us a proof of the original Hardy-Littlewood maximal inequality. And the reason why is because we no longer have this nice covering lemma that says by picking maximal balls, we can partition E lambda nicely using balls from our collection. So that was a very unique property to dyadic cubes. And it's for this reason that we're going to need covering lemmas specific to balls, so we can come as close to doing this as possible. So in the next video, we'll cover one of these covering lemmas, the 5R covering lemma.